Today, I'm going to take you through the story of the invention of the telescope, how it happened, and the surrounding events. About 100 years before the time of Galileo, eyeglasses were introduced into Europe. What made eyeglasses possible was making clear glass. Up until that time, the glass always had contamination in it. It was dark or colored or something like that. It was not clear enough, clear like water. But finally, about 100 years before Galileo, probably a little bit a little bit before the time of Copernicus, people learned how to make clear, water-clear glass. That's quite a story in itself, but we're not going to go into it. But as soon as they could make glass, they could then grind and polish the glass and make lenses. And there are two kinds of lenses that are commonly used in eyeglasses. One kind of lens is the so-called negative lens or concave lens, and it looks like this. It's a piece of glass that is skinny in the middle, fat at the edges and skinny in the middle. If you look through it, it makes the things that you look at seem smaller than they really are. And here I have an example of such a lens. Here's a negative concave lens. And if I hold it up in front of this, I suppose you'll see right away that it makes things look smaller than they really are. Artists, when these first came out, artists used to like to use them because they could look at a landscape scene and see it reduced, and they thought, well, that's the way it would appear on the canvas, smaller. And so they like to look at the world through these lenses. But the main use for these lenses is for people like me, or is it like people like me, that can only see things that are near. And it's called nearsighted people. Maybe it comes from reading too many books. Who knows what it comes from. But if you put a lens like this in front of your face, you can see things in focus that are far away. See, normally I can only see things near in focus, but with the aid of this lens, I can see things far away. I'm nearsighted. And these glasses that you see me carry on the end of my nose every day, these are two negative lenses like this. Now, there's another kind of lens, and it's called a positive lens or a convex lens. And this kind of lens looks like this. And this lens is fat in the middle and skinny at the edges. And of course, I have an example of that kind of lens too. Here's that kind of a lens that is fat in the middle and skinny at the edges. And it will do just the reverse of what the concave lens did. Instead of making things smaller, this lens will make things bigger. And I'll put it up in front of this thing, and you can see that it's probably magnifying a little bit. This lens will also do something else that's even more interesting than magnifying. It will focus. Here you can see on the blackboard the image of 3 overhead lights. So you can make an image of the sun and start a fire with this kind of a positive lens too. The other kind of lens that I showed you, the negative lens here, I hold it up and it will not make an image of the overhead lights. But indeed, this lens will make an image, and you can use it as a burning glass. But it also has a medical use. It's used for people who can see things far away but can't see things up close. Those are called farsighted people. And if they want to see things up close, like the telephone book, then of course you can use this as a magnifier and you can read the telephone book. But when you drive your car, you probably don't need this kind of a lens because it's for farsighted people. This is usually used by older people, maybe people who never had to use glasses in their life until they got old. these lenses, of course, the positive lenses and the negative lenses come in varying strengths, depending upon how bad your eyes are. And I will, just for the heck of it, draw how you would make these lenses of various strengths. First of all, the negative lenses. Well, you could have very weak negative lenses that were just, they're almost flat like this. But they're just a little tiny bit skinny in the middle. And then you can have stronger ones that are, see, this is more of a variation. And then you could have extremely strong negative lenses that are like this. And they don't, I drew them bigger, but they don't have to get bigger. And the same with positive lenses. You can have a positive lens that's just a little bit fatter in the middle than at the edge, just a tiny bit fatter. Or you could have one that's a little more fat in the middle than at the edges. Or you could have a lens that's enormously fat in the middle. Okay, so these lenses are depending upon what you need. Now, I have exaggerated those. When they're used for eyeglasses, you never get ones that are have this much bulge in the middle, or ones that are that skinny, but there's quite a variation among what different people need. And in the olden days, if you went to get eyeglasses, say in the days of Galileo, you'd go to a store and they would have the negative lenses in one bin and the positive lenses in another bin. And of course, what you would simply do is you would pick up the lenses one at a time and try them, and then you'd pick up another lens and try it, and pick up another lens. And pretty soon you'd zero in on the lens that worked best for you, and they would be made into a pair of spectacles for you. And of course, there would be one set of negative lens bins and another set of positive lenses of various strength in a bin. Now, undoubtedly, somebody who came to buy lenses would also bring along their young kid, would tag along with them, and like kids have done for hundreds of years in stores, the kid would begin picking up things and playing with them. And of course, since the kid has two hands, naturally he's going to pick up two things. So he's not only going to pick up a negative lens, the kid's going to pick up a positive lens with his other hand. Yeah, I'm sure if the kid had three hands, he'd have three lenses, but most kids just have two hands. If you do this, the kid's going to see his parent, trying the lenses. So naturally, the kid's going to do the same thing. The only thing is that the kid has two lenses in his hand, and so the kid's going to hold them both up. So the kid's going to do this. Or the kid's going to do this. See, there's only two possibilities with this. You can put the negative lens near your face and the positive lens out further, or else you can put the positive lens near your face and the negative lens out further. And by one of these means, you're going to come to a remarkable invention, one way. Now, if you're the kid making this discovery, your chance of making the discovery on the first try is exactly 50%. Isn't that right? You get it the right way. And if you don't get it the right way the first time, then the chance on your second try of getting it comes 100%. So it's a discovery that must have been made many times by many kids in many stores, wherever lenses were sold in all the major cities over Europe. Undoubtedly, this was discovered many times. Now, we're even going to rediscover it right now. I'm going to go up to the camera, and I'm going to hold these lenses in my hand. And to make sure that I hold them straight, you don't want to hold them tilted, I have two lens holders here, so we'll make it very analytic-like. I'll hold this lens here. That way I can tell that it's held squarely. And I hold this lens squarely here. And I'm going to go up to the camera, and you'll look at the blackboard, and I will put these lenses, see if they're in there straight, yeah, more or less. And one way you'll discover the telescope, and one way there will be no telescope. So let me put on my glasses so I can see what I'm doing now, and come up and try the experiment. Now, the first way I'm going to put the positive lens, the fat middle lens, near the camera, and the lens that's thin in the middle, away from the camera. And we're just going to look at the blackboard and see what we can see. I'll put one lens right up there. Okay. And things are a little bit blurry. Things come into focus, and then they're into focus, but they get kind of small. Okay, this clearly is not a telescope. Now I'm going to put the lenses the other way. Now I'm putting the negative lens the nearsighted lens right up near the camera and the positive lens away. And behold, holy cow, it's magnifying like mad. There we can see the very bottom of one of those negative lenses and the top of a positive lens. So you see you're getting magnification. Indeed you are. Wow, it works. Okay, again you can see it the other way around, interestingly enough. You can see how a star sees the astronomer. I'm going to do exactly the same thing, only I'm going to do it looking at the camera. First I'll put the positive lens, the convex lens, near me, and the concave lens I'll put out, and I bet you can see my eye getting small, and I can see the camera also getting small. And now I'll do it the other way. I'll put the negative lens near my eye, the one that's thin in the middle, and the one that's fat outside. I'll put it away, and I see the camera magnified, and I'll wager that the camera sees my eye just as magnified as I see the camera. So it's a fairly easy thing to discover. And since it's so easy to discover, you might ask why it took 100 years after lenses were found, after lenses were commonly available before the telescope was invented. Before I go on to that, I want to make one point. You notice that when I had the telescope in front of the camera and I magnified the lens, I magnified the blackboard, while the blackboard became magnified, there was also, which was an advantage, there was also a disadvantage that came in. You notice that we could only see a very small part. When I showed them, we could only see a very small part of the whole blackboard. We couldn't see everything on the blackboard magnified. When I magnified, you could just see this little region here. And that's a problem that telescopes have from the first day they were invented, and it is a problem that remains even to this day with the biggest telescopes in the world. The 100-inch telescope, the 200-inch, the space telescope. They're all cursed by this problem that though they have wonderful magnification and can produce very clear images, they can only see a very small part of the sky. And in fact, very often a parent will want to encourage a kid to be interested in science and will buy the kid a telescope for Christmas. And the kid will, of course, be fascinated and take the telescope outside and try to look at something in the sky with it. And very soon, will be frustrated and will cease using the telescope. And the reason for this is that the telescope is able to see only a very small region of the sky. And so when the kid tries to aim the telescope at something in the sky like the moon, he can't do it. And then he tries again and tries again. Maybe he gets lucky and he succeeds in doing it. But since the telescope sees such a small area of the sky at one time, it's very hard to aim it. And it's very likely to frustrate a young kid very quickly. So that's a problem that you might appreciate if ever you see a kid struggling with a telescope. The telescope was probably invented many times, or discovered, I should say, many times. It was discovered many times. Why did it take so long to do it? Okay, the reason is this. In the olden days, the days of Galileo, the days of Copernicus, the only way a tradesman had of protecting an idea was secrecy. So everything that was of use was held in secret. Now I want to tell you that the telescope is a very useful thing. And I'll tell you what the principal use of a telescope is in a practical sense. It's not for studying the stars or looking at a football game. Let's think of a battlefield. One of the most difficult things that a general has at a battlefield is controlling a big array of soldiers. The soldiers are spread out and over a big field. And you can't see which is your soldier and which is the opposing soldier. And what do they do about that? Well, a long time ago, the idea was invented that the soldiers should wear uniforms and carry flags. The purpose of the flag is so that you can tell which is your soldier, which is the other soldier. Imagine a situation that there's some soldiers appear over a hill where you didn't expect them. And the first thing the old general asks is, are they our soldiers or are they the enemy soldiers? And very often next to the old general, there's a young second lieutenant with keen eyes, and he looks and has much better vision than the general. He says, "They're ours." That's great jubilation. Or, "They're theirs." And oh, it's a bad situation. Now imagine that one of those, that general that was trying to command his army visually has a very poor telescope. Just imagine it's a 2-power telescope, which means it makes the things twice as large. The kind of a telescope you used to get for free in a Cracker Jack box. Rotten, useless, toy-like telescope. But it enables you to magnify 2 times. And one general has that and the other doesn't. Can you see what an advantage it would give him? He would be able to identify, to command, to control his troops at double the distance of the general that did not have the telescope. For those generals who had telescopes, even the crudest kind of telescope when they were first invented, it gave a fantastic advantage over the other general who did not. It's almost a situation like World War II in the Pacific, where the United States had radar and the Japanese didn't have radar. There's no amount of gunmanship, of heroism that can counterbalance an advantage like having radar against an army that does not have a radar. So it was with the telescope. Let me give you another example. At sea, when 2 ships meet, they want to know if they're friend or foe. The sooner you can make that identification, the better. Because if you see that the ship out there is an enemy, you want to run as fast as you can, if you can run, because if that ship can go just a little bit faster than your ship, then it's very hard ever to escape, because if that ship can go a little bit faster and it's a long ways to a safe harbor, the other ship that can go a tiny bit faster will eventually catch you. So the sooner you can tell if you should flee or not flee, it's very important. So how do you tell that? Well, you look at the other telescope and you try to identify its flag, or maybe you can identify the ship itself. So it's very important from a practical sense to identify the other ship, if it's friend or foe, at the greatest possible distance. Now again, imagine the situation that one sea captain has a telescope, a very cheap telescope, a very poor telescope, just a 2-power magnifying telescope. But the other ship does not have a telescope at all. And you see what a fantastic advantage the ship that had the little telescope would have over the ship that did not in identification. So it's a fantastically powerful and useful thing. Incidentally, did Columbus carry a telescope on his ship? No, the telescope hadn't been discovered yet, or wasn't widely known. Columbus did not carry telescopes on his ship. So what would you do in this case, in a world like this? What you would do if you were a general or an admiral and you found some man who learned how to make telescopes, the first thing you would do is you would buy all the telescopes he had. And the second thing you would do is you would buy all the tools that he had for making telescopes. And the third thing you would do is you would swear the man to secrecy, that he would never make a telescope for anybody else except you. And the fourth thing you might do, if you wanted to be very careful about the whole thing, would be to come back at night and kill the guy. That way you'd ensure that he couldn't make any telescopes for anybody else. So now that kind of illustrates why it is that telescopes, the story of a very useful thing, got around Europe very slowly. Everybody kept important things secret. You know, if somebody tells you something, the information is probably at best useless, and in all likelihood it's probably actually misleading. You can think about that with the people at school that want to tell you so many things. You say, well, nowadays, of course, people will tell you that important scientific discoveries cannot be kept secret, isn't that right? Because everybody can discover them. And that's true, but it takes a while. But I want to tell you that the invention and the making of these lenses was not a scientific secret. It was not a scientific secret. Why not? Why it was a secret of tradesmen. How do I know that? I know that by the very name lens itself. You know where the name lens comes from? The name lens comes from the shape of a bean called a lentil. Have you ever actually seen these beans called lentils in the store? They're shaped just like positive lenses. Now, that shows that the development of optics was not in the hands of scholars and university people, but was in the hands of tradesmen. Because if a university man was dealing with a lens, he would give it a Latin name, 3.5 miles long. Isn't that right? He would not name the thing after a bean. The man who would name it after a bean is some sort of a blue-collar man who was working in a shop. And telescopes were developed by craftsmen, not by scientists. In fact, the whole beginning of optics was entirely by craftsmen and not by scholars and academic people and scientists. They were latecomers to the story of telescopes. Well, now, after Galileo found out how to make a telescope empirically, just like the kid, after you find out how to make it, Galileo, though, was a scientist in his heart and his soul. And the important thing to a person like Galileo is not only how it works, but even more important than how it works, it is why it works. What makes it magnify? What makes it magnify? That's what Galileo would wonder, and that's what I want to tell you. I want to give you what I believe was Galileo's own explanation of how a telescope magnifies. Before I do that, let me tell you how it would happen now, how it would be explained now. If you were to take a physics book, say even a high school physics book, certainly a college physics book, and open it up to the section on telescopes, they would describe a single lens and give the equation for the images that a lens makes. A lens is able to make images. Remember, I showed you that here is the image of the overhead lights, and there are equations that control how big this image is and how far it is away from the lens, depending upon how far the lights are overhead, away from the front of the lens. And you would deal first with the equations of the lens, and after you dealt with the equations of the lens, then you deal with the equations of this lens, and finally they would deal with the equations of the two lenses combined. And when you dealt with those equations combined, lo and behold, out by a bunch of algebra would come how a telescope magnifies. Or else you could do it, there's another way to do it where you explain a lens geometrically, how the light comes into a lens and how it comes out and how it's focused and this and that, and then you combine two of them and you would explain it that way. But in the days of Galileo, all the lens theory had not been developed. Lens theory was to be developed later. So they didn't have a mathematical way of explaining lenses or even a geometrical way of explaining lenses in the day of Galileo. So how could Galileo explain how a telescope worked? I would like to give you now what I think was Galileo's own explanation of a telescope. By the days of Galileo, people had a very good idea of how eyes worked, human eyes and cow eyes. In fact, Leonardo was quite into dissecting people and animals, and so he knew very well how eyes worked, and the people who follow him, who read his books, knew how eyes worked. And an eye works, this is essentially a simplistic idea of how an eye works. An eye is a little ball here, and there is a lens in front of the eye, and here's the lens that's in front of the eye. And what happens is that this lens makes a picture on a screen. Back here is a screen. This is called the retina, and this is the lens. And out here is some sort of an image of an object in the outside world. And the eye sees that, and the eye makes an image of that on the back. And of course, the image is upside down too, you know that, and the brain turns the image right side up. But that's basically how an eye works. Galileo would speak to himself in the following way. Galileo would say, well, I want the thing magnified. Well, so how can I get the thing magnified? Well, what does it mean to get it magnified? Well, what magnification means is that this image in the eye, this arrow that's on the back of the eye, on the retina, should be bigger. It should be bigger. So Galileo would think to himself, how can I make this bigger? And he would say, well, here's one way to make it bigger. Just imagine a bigger eye. If you imagine a bigger eye, a bigger lens in front of the eye, then everything is scaled up. And here, back here, the same thing comes in, but now, lo and behold, the image is twice as big. So assuming that the eye is twice as big, everything is twice as big. So Galileo could say, listen, I know how to get things magnified. Get a bigger eye. If God would take my eye out some night and put a cow's eye, which is twice as big, let's pretend, in place of my eye, then I could look around and see everything magnified times 2. But of course, you can wish and wish and wish, but that will not happen. God will not put a cow's eye in your place. Then Galileo began to think. He said, well, listen, maybe I got an idea. Maybe I don't really need a whole cow's eye. Maybe I could do something else with my eye. And Galileo began to think like this. He said, this is an idea I've got. And here I'll draw the original eye. And Galileo said, well, I'll take my eye like this. And there's another copy of the same drawing above with the lens. And Galileo said, listen, what I'm going to do, I wish that I could have an eye that was like this. See? I wish I could have an eye that was bigger, just scaled up. I wish I could have an eye like this. But I got an idea. I am going to take the lens out of my eye, so there'll be no lens in my eye, and just put a lens out here by itself. Now maybe it will be a lens from a cow's eye, or maybe it will be a glass lens I'll make, but then the effect will be exactly the same as if I had a cow's eye. It'll be exactly the same thing, only the image will fall on my retina, which is lucky because my retina is attached to my brain. I can see the image. Of course, there's a little problem with this, because if you truly did have the cow's eye here, you'd have a big image, but you'd also have a big retina. See, you'd have a big retina. Here, with this setup, using your eye, you still have the big image, but you only have a small piece of the retina. So what does that mean? That means that you cannot see the whole picture. In other words, you can only see a little bit of the center of the scene. All this part that the cow could see, the wide scene, is cut off, and you have a very narrow field of view. It's like looking through a pipe, which is exactly the problem we saw before when we made the telescope. You couldn't see the whole blackboard, you could only see a little bit of the blackboard, and that's the curse of the telescope. But if you're willing to live with it, and you're also willing to cut your eye, the lens from your eye, and out here put another lens, well then that's okay. It will, in theory, work. But then Galileo must have thought about this. He says, hey, do I really want to cut and remove the lens from my eye? I don't want to do that. You know, you could get a heck of an infection cutting your lens out of your eye and leaving it open like that. He says, I'm not going to do that. That's unthinkable. The heck with it. There's something you can do that has the same effect that occurred to Galileo. And I want to show you what it is. If I draw this picture on the blackboard, and I say, well, now, and I say, what is this? Is this a lens? See, it's convex. It has a flat side, but it's convex on one side. Is that a lens? You say, certainly. What kind of a lens? A positive lens. It's a magnifying lens. And if I drew a picture of this over here and ask you, well, is this a lens? You'd tell me, yes, that certainly is a lens. What kind of a lens? Well, that's a lens that makes things smaller. That's a negative lens, a lens that's skinny in the middle. That's what kind of a lens that is. Then suppose I drew this down here and said, now what is this? Is this a lens? It's just flat on both sides. You'd say, no, that's not a lens. I'd say, well, what is it? You'd say, well, that's just a window. It's a flat piece of glass. You don't call a flat window a lens. But I want to show you something. Suppose you take this lens, positive lens, and this negative lens, and you put them together like this. Just stick them together. What have you got? They combine, they fit together snugly, and what have you got? A window. A positive lens and a negative lens combined in the right way cancel out to no lens. And undoubtedly that's where the name positive came from. Do you ever think, why do they call a positive lens positive? Because it says so in the physics book. That's how most people, that's supposed to be knowledge. But no, there must be a reason why they call it positive. And they call a negative lens negative. There must be a reason they call it negative. And the reason is that a positive lens can be combined with a negative lens, and just like a positive number and a negative number, they will cancel each other out. They'll cancel out. And Galileo knew enough about lenses to know exactly what I told you. Didn't know the equation, but he at least knew why a positive lens was called positive, which is more than a lot of people do today who know the equations. Now, so Galileo said, now, here is my eye. I previously thought maybe I would cut my eye lens, the eye lens out of my eye, but I don't want to do that. I surely don't want to do that. But there's a non-surgical way to do the same thing. And the non-surgical way to do the same thing was this. Here's the eye lens. The non-surgical way to do it is to combine this with a negative lens. And here's a negative lens of just the right strength, And that will have effectively, then it'll be like your eye had its front lens removed. Then over here you can put in this lens over here, an artificial lens, maybe made out of glass, and there it is. And then you can take these two things and hook them together like this. And then we don't really need this because this was just the imaginary cow's eye. We'll take it away. And your eye can go away too. You can take your eye away. And what do we have left here? A negative lens with a tube and a positive lens at the other end. This is Galileo's telescope. This is a Galilean telescope, or it's also the same design that's used in opera glasses. And in fact, this lens back here, nowadays it's called the eye lens because it's near the eye, and this is the object lens, I suppose, because it's near the object you're looking at. But the old name for the eye lens, if you look back in Latin, you find it's not called the eye lens, it's called the neutralizing lens. You say, what in the hell is it neutralizing? It's neutralizing the lens in your head. So there's the telescope, and there's the story of how Galileo reasoned it out. I want to ask you a question. I have a telescope on the blackboard here. There's an eye. Okay. And here is a telescope it's looking through. And there's the back. And over here. And there's the objective lens in the telescope. And now, there's a telescope with a positive lens in front and negative lens in back. Human eye looking through it. What's the magnifying power of that telescope? That's my question to you. What is the magnifying? Well, the answer is, well, we need an equation for magnifying power, and you haven't given any equation. You haven't given any equations at all. So without an equation, how can I come up with what the magnifying power is? Well, the equation is just sort of an ignorant summary of the story, and you know the story. So if you know the story itself contains the equation. You don't need an equation. Equations are only for nerds. For people like Galileo, the pictures talk. How can you make this picture talk? Well, what you have to remember is the story. Here you see the eye of the human being looking through the telescope, but you have to remember the imaginary giant cow's eye. So let's put that in. This is the lens here, and then in our imagination we draw in the cow's eye. I don't think we'll be able to fit it all on the board, but we finish enough of it. And the story, of course, is that the cow's eye, this big cow's eye, should be thought of as nothing but a magnified human eye. And in fact, so let's see how much bigger the cow's eye is than the human eye. Well, let's take its diameter. There's one human eye. That's from the back to the front of the human eye, the retina to the lens. Now let's do it see how many human eyes fit in the cow's eye. 1, 2, 3, 4, 5. See? This cow's eye is about 5 times the diameter of the human eye. 5 times the diameter means 5 times the magnifying size. So we have here a 5x telescope. 5 without any equation, because the picture does the talking. So, incidentally, I want to tell you a little bit about what's meant by the magnification of a telescope. If you look at something and it's magnified 5 times, that means if you look at a person and the person appears this tall to your eye, naked eye, then when you look at the person through the telescope, the person will appear 5 times taller. Isn't that right? So 1, 2, 3, 4. Well, I'll put 1 down. 5. So the person will look this tall through a 5-power telescope. That's supposed to be 5 times as tall. That's what's meant. Sometimes you find a company. I saw a Macy's ad once for a 100-power telescope, a little telescope, a little tiny telescope. They said it was 100 power. I said, how could that telescope be 100 power? But what people do sometimes is they do this. If a telescope, if there's a box, and the telescope is, say, a 2-power telescope, which means now the box is twice as high. It's also twice as wide, isn't that right? See, if you magnify one dimension by 2, you magnify the other dimension by 2, and if they want to mislead you, they can say it's not a 2-power telescope. They can say it's a 4-power telescope. But that's not how telescope power, you should call it a 2-power telescope. They want to cheat you, they'll call it a 4-power. You can also play that game in another way. You could say, look, here's a box. There's a little box that's seen through a 2-power telescope. And you could say, now how would that little box look as if it was, here's a little box that's seen by the naked eye. Now how would the little box look if you saw it through a 2-power telescope? Well, you could say that'd be the little box. It would be now twice as wide, twice as high, and it would also be twice as deep. Isn't that right? So you could say, gee, through a 2-power telescope, the box would be how much bigger? It would be not 4 times bigger, so you could say it was 8 times magnification, but that's cheating. It's only really double magnification. It's not 8 times. Now, if you could have 4 dimensions, you could play the game even further. Now I want to go on. I've got more things to tell you. We got into this, of course, because we're following the footsteps of Galileo. And Galileo, the significance to the telescope to him was not that it enabled him to see the heavens bigger or to see them closer up, but the significance to Galileo of the telescope was that when he saw the things in heaven, he saw that they had characteristics that made them like the things on earth. In other words, the things in the planets that he looked at had characteristics like the earth, and the earth had characteristics like the planets, which meant that Copernicus's idea that the things out there were like the things down here had validity to it. Remember the things you saw. Jupiter had moons. Our moon had mountains. The sun had spots. There were imperfections in heaven. The sun turned on its axis just like the earth turned. And so he saw all those things, and that made him convinced that Copernicus' idea was right, that the earth was like a planet, and that the earth and the planets were like the earth. Galileo had one problem, one huge problem with convincing people that his idea was correct. You see, Galileo was not only a scientist, but he was also a bit of an evangelist. And he was evangelizing not on a religious belief, but on a scientific belief. But he was trying to sell his idea. But he had one problem, and that problem was that at the time that Galileo lived, Aristotle was still held in very high regard. Now, I have to explain a bit of a story about that. Who was Aristotle? Aristotle was an ancient philosopher. In fact, more than a philosopher, perhaps he was an encyclopedist. What I mean by that is he wrote about all kinds of things. Aristotle wrote about astronomy, he wrote about physics, he wrote about chemistry, he wrote about biology, he wrote about politics, he wrote about sex and love, he wrote about geography, he wrote about business, he wrote about every subject there was. And he wrote so much that even though maybe 9 books out of 10 were destroyed in the Middle Ages, he wrote so much that some of his books survived. And he turns out probably to be one of the best known ancient Greek philosophers. And at that time, the time that Galileo lived, philosophy was particularly important. You know, if you go to school now, one of the most important things you study, perhaps the most important thing you study, is science. But back in the days of Galileo, the most important thing that you studied when you went to school, the number one subject was philosophy. And in fact, to this day, it's curious that if you go through school and you get the first degree, what's the first degree? BS, bullshit, isn't that right? And then you get the second degree, MS, what's that? More shit. And then finally you get PhD, third degree, piled higher and deeper. What does PhD means. It means a doctor of philosophy. That's an amazing thing. The guy might do his work in biology, but he's not called a doctor of biology. He's called a doctor of philosophy. He might do his work in economics. He's not called a doctor of economics. He's called a doctor of philosophy. Not called a doctor of physics or astronomy, but a doctor of philosophy. It's a leftover thing from the ancient times when it was an honor to be called a philosopher. That was the ultimate expression of honor that somebody could give you, is to call you a philosopher. And so they confer that honor on all these people, even to this day, hundreds of years later. Now, at the time that Galileo was active, philosophers ruled the universities. And of course, the number one, the philosopher that everybody studied was Aristotle. Aristotle was the king of philosophers. And Aristotle's view was essentially the pre-Copernican view. Aristotle's astronomy was Ptolemaic astronomy. Aristotle's astronomy had the Earth parked in the middle of the universe, and then around the Earth moved the planets and the sun and the moon and the stars, and the Earth was fixed in the center. Aristotle's physics and Aristotle's astronomy was the old physics and astronomy that I described in my first lecture with the earth, air, fire, and water. The people said to Galileo, they said, Galileo, you know, you're very smart, your theory is very convincing, but you differ with Aristotle. We have to make a decision. Are we going to believe Galileo's view of the universe, or are we going to believe Aristotle's? Now, in those days, Aristotle had a lot of authority. Moreover, when you saw Aristotle, you saw Aristotle as a marble statue or as a picture in a book. Aristotle, as a marble statue or as a picture, appeared like a god, like an old Greek god with a sheet wrapped around him. Galileo, if you went to see Galileo and looked at him, he was a man. He was probably a horny old man. Certainly, his teeth were probably bad. He probably had bad breath. And he probably had spaghetti stuck in his red beard. He appeared to be a very mortal creature. Now, if you're not very smart and you make your decision not on logic, which few people do, but on authority, you say, well, which of these two very smart people should we believe in? They differ. Probably the conservative thing to do was to believe in Aristotle. And so a lot of people would not believe Galileo explicitly because he differed with this very important figure, Aristotle. And Galileo knew that. And so what is he to do? Usually, two people could have a debate. But scientific debates, they never decide anything because you don't understand what they're talking about. The kind of a debate that really does decide things is when you say, well, believe me, don't believe that guy because he's a bad guy, or because he's dumb or mean. Well, just because somebody is a bad guy, you know, that in itself that's maybe people like bad guys. He's the head of the pack. When you're arguing, but those are the kind of arguments that are effective, not arguing against a person's ideas, but arguing against the person himself. Now, there's two ways to argue against a person, or there's one way to say the person's bad, but there's a much more effective way to argue against a person, and that is to make the person appear to be a fool. If you can tell a joke or a story or make the crowd laugh at your opponent, that is the most devastating thing you can do in an argument, to make the other side appear to be foolish. And that is what Galileo did, and I want to tell you how he did it. As I told you before, Aristotle wrote many, many books. And when you write many books and many things, you have to say many things. And when you say many things, you're liable to say something that isn't quite right. And Galileo realized there were some things that Aristotle had said that were clearly not quite right. And this is the thing that Galileo picked on. Aristotle, in one of his writings on physics, described dropping objects. And he said, if you drop an object that's heavy, like a big rock, and an object that's light, like a chicken feather, if I drop a rock and a chicken feather, which is going to hit the ground first? And the answer is, of course, the rock's going to hit the ground first. And you could just leave it at that. But Aristotle had to write books, so he had to fill up many pages. So then he went on and he said, well, now look, if you drop two objects and one object has half as much weight as the other, then the object with half as much weight will take longer to hit the ground. And if it has only half as much weight, it will take twice as long to hit the ground as the other object. And if you have two objects and one object has only 1/10 the weight, only 1/10 the weight of this object, then it will take 10 times as long to hit the ground. If it has only 1/20 of the weight, it will take 20 times to hit the ground. Well, it is true that heavy objects hit the ground before light objects, but it's not true that if one object weighs only 1/20 as much as another object, it takes 20 times as long to hit the ground. That's not true. Galileo knew it. And in fact, Galileo realized that if you have objects that are heavy, so heavy that the air can't mess them up. Now, chicken feathers get messed up with the air, but if you have objects that are so heavy that they cut through the air without much resistance, then in that case, the heavy object and the light object will hit the ground in practically the same time. And to make a fool out of Aristotle, Galileo did the following thing. At a big university, and Galileo was at the university in Pisa, at noontime, just like at noontime today at a big university, kids you're looking for some entertainment. They watch the dogs screwing each other, or they listen to a political speech by some radical, just for the sake of entertainment. They're looking for entertainment. So Galileo said, today I'm going to give you some entertainment at lunchtime. Come to the Leaning Tower of Pisa. And so he took a big crowd of his students and probably a whole bunch of followers to the Leaning Tower of Pisa. And then he went up the tower and he said, here I have two melons, two great big watermelons. One melon is a 30-pound melon, and the other is only a 15-pound melon. I'm going to drop these two melons off the Leaning Tower. Okay, which should hit the ground first? Well, of course, the heavy one should hit the ground first. Now look at your page 37 in Aristotle. Of course, Aristotle was a compulsory course in those days. You had to study Aristotle. You know, kids don't love their compulsory courses, but everybody had the books. They open up to the page, read it. How much longer will it take the 15-pound melon to hit the ground? It should take twice as long. Okay, let's see. So Galileo goes over to the edge of the tower with the two melons and he drops them. Well, it's a big crowd. There's no stopwatches. How can you tell which one hits first? You know, it's a lot of screaming and a lot of yelling. Galileo is smart. He drops them on big upside-down garbage cans, so they make a big boom when they hit. So now you know if they fall, if he drops them at the same time and they hit at different times, you're going to hear boom, boom when they hit the garbage cans. But if they hit together, it's just kaboom. So he drops the melons. Kaboom! Oh, great, Galileo, we love it. You made a fool of Aristotle, and we hate that course anyway. It's compulsory. All right, so that was really great. He made a real impression on the crowd. He showed that Aristotle was not infallible. Aristotle is Greek god who had marble statues. You know, there were statues of Aristotle all over the university, or in every university. In fact, there still are in public libraries. You can see a marble statue of Aristotle. Common thing to see in a public library. But the man was not a god, even though he had marble statues of himself. By the way, Galileo not only made friends that day by impressing many people that he was smarter than Aristotle, but he also made enemies. His enemies were the philosophers. You see, to the philosophers on campus, Aristotle was their hero, just like geometry teachers like Euclid, English teachers like Shakespeare, philosophy teachers to this day like Aristotle. And the philosophy teachers had it in for Galileo. And eventually it was they that got him. It was the philosophy teachers who sicked the people on Galileo during the Inquisition to get him in trouble as revenge for what he did right then and there. But of course he was in trouble much sooner than that. Right away he was in trouble. I think he didn't get seniority at the university where he was teaching. I think that he didn't get tenure, and the next semester he was looking for a new job to teach in a new place. But he did make one hell of an impression on the student body that day at noontime when he dropped the melons from the Leaning Tower of Pisa. I want to tell you what happened that afternoon. That's what happened at noontime, but I want to tell you what happened that afternoon. At 1 o'clock that day, after he put on his demonstration at noontime, Galileo taught his regular physics class, and he had most all his students showed up that day since he put on a good show. And they said, Prof. Galileo, that was fantastic. That was a great show. Let's give Galileo a hand. Okay, and they all clapped for the demonstration with the melons in the garbage can. But one kid, who must have been a smart kid, said, Prof, I got a question. I agree, you're right, Aristotle was wrong, but why was it, Galileo, why was it that the heavy melon fell first? Or, excuse me, why wasn't it that the heavy melon fell first? After all, there was more force on the heavy melon. Gravity pulled it down harder. If gravity pulled the heavy melon down harder, why didn't it hit the ground first? Could you please explain how come the heavy melon hit the ground at the same time that the light melon did? And Galileo said, that's a good question. You should always wonder why these things are. And I'm going to tell you why. I'm going to tell you why it is that heavy rocks and light rocks hit the ground at the same time. And this is Galileo's explanation that he gave at 1 o'clock that day. Galileo said, what is a big rock? You know what a big rock is? A big heavy rock? A bunch of small rocks glued together. And you should think of the big rock as a whole bunch of rocks falling together. A whole bunch of smaller, lighter rocks falling together. It's like two people jump off a cliff. If two people jump off a cliff, each one falls at a certain speed. Now, if they hold hands, they have a body that weighs twice as much as any one of them. Are they going to fall any faster if they hold hands? If they wrap around each other as they go down, are they going to fall any faster? No, they're not. So each individual rock in the big rock falls at the same speed, and that was Galileo's explanation of why light bodies and heavy bodies fall at the same time. I'd like to go a little bit into that and show you where Galileo got that. It's a very clever explanation, isn't it? And I would like to show you where Galileo got that idea from. Galileo was of the opinion that things in the world were made of little particles. And these little particles have had all different names. Sometimes they're called atoms, molecules, corpuscles. Let's call them atoms. I'm not sure that was the name they had in Galileo's day, but he had the idea that the world was made of little atoms. And if you take that point of view, then what is a big object? A big object is nothing but a whole bunch of atoms stuck together, isn't that right? So if any little atom falls, then the big thing will fall just because all the little individual atoms inside of it are fall, but the big thing shouldn't fall any faster, any slower than any of the individual atoms of which it's made fall. And that was Galileo's view of the world. You might say, well, how did Galileo know that the world was made of atoms? He must have been very smart. Well, he couldn't have been, because he didn't know there was centuries and centuries of discovery after Galileo that led to the modern view that the world is made of atoms. So where did Galileo get the idea from? He got the idea in the following way. Remember, Galileo was not an astronomer, or maybe he was an astronomer, but he was not an astronomy teacher. He wasn't officially an astronomer. He wasn't even officially a physicist. Officially, Galileo was a geometry teacher. That's what he was. That's what he was paid to do. That's what was written on his door. That was his main business, geometry. Now, in geometry, we talk about things like solids, like a cube. Here's a cube. But what is a cube made from? A cube is made from various flat surfaces. But what are flat surfaces made from? The flat surface is defined by various lines. But what is a line made from? A line is nothing but a whole bunch of points glued together. So Galileo had the idea that in geometry, all geometric figures are made of points. And then Galileo also had the idea that the real world, the physical world that we live in, is based on the mathematical world, that the physical world must be made in the image of the mathematical world, in exactly the same way that people believe that people are made in the image of God. That same idea applied in Galileo's head, that the physical world is made in the image of the mathematical world, and therefore, if the mathematical world is made of points, then the physical world also has to be made of points, and he named those points atoms. Now I say, ooh, is that very smart, or is that, what kind of is that? Well, that was his logic. The logic is not entirely solid, but that was his logic. I would like to show you a little defect in Galileo's logic, a little problem with it, because you might think it's very clever, and it is very clever at one level, but don't be carried away with Galileo's logic, and I'll show you why. It's very nice to follow through on Galileo's thoughts. He's a very smart man, but not so smart that we can't look at his thoughts rather thoroughly. Here are two lines, a short line and a long line. And I would like to ask you a question. Which line has more atoms in it? You say atoms of what? Well, atoms of chalk. Obviously, the long line has more atoms in it. How many more? About twice as many more. Now, which line has more mathematical points in it? You'd tend right away to say, oh, the long line has more points in it. How many more? Twice as many points. But that's not so. And I'll show you why. You can make a rule called a one-to-one correspondence, and you can show that there are exactly as many points in the long line as the short line. And I'll show you how it works. What you do is you first draw a line like this along the bottom, and then you draw a line through these two top points like this. And this makes a point over here that we'll call O. It looks mathematical that way. Now suppose you choose some other point, and we'll call it A on the short line. For every point A on the short line, you can draw a line from O to A, and it will go over to here. And we'll call this point A over here. So for every capital A, there's a little a in the long line. Now suppose I pick some other point in the long line, call this B, point B. Again, I can draw a line from B over to O, and I'll find a point B over here in the short line. So for every point in the long line, there's a point in the short line. For every point in the short line, there's another point in the long line, which means that there has to be as many points in each of the two lines. So you can see that the idea of a mathematical point is different from the idea of an atom. But Galileo didn't realize that. He thought that they might be the same idea. And even though it was the wrong idea, it led to the right answer, because it made him think the world was made of atoms. That led him to realize that a big rock was nothing but a whole bunch of little rocks glued together. And then the big rock should fall no faster or slower than the individual little rocks, which means that heavy and light objects fall at the same speed, which is correct, and that's Galileo's view of the situation. But that is not the end of the story. That question of why heavy objects and light objects fall at the same speed has troubled many, many thinking people for a long time. Many, many, many thinking people have been troubled by that idea. And I would like to tell you another true story about that. Years ago, when I first learned this, it seemed very interesting to me, and when you learn something new, it always seems so interesting. And I went to decide I was going to educate my sister. I have a sister, Elise. And I still remember in the afternoon I went to give Elise a lesson on heavy objects and light objects and which would hit the ground first. And I captured Elise's attention. And then I asked her, I said, Elise, and I probably had two cans, maybe a heavy can and a light can. And I said, if I drop these two out, remember Elise was a girl, she was probably in the grammar school. Maybe she was in the 3rd grade, not much older than that. 3rd grade girl. And I said, if I drop this heavy object and this light object, which is going to hit the ground first? And naturally, I expected that Elise would tell me that the heavy object would hit the ground first, and then I would tell her all about Galileo. But Elise said something remarkable. She said, Louis, the light object will hit the ground first. The light? I said, Elise, I didn't expect that answer. I said, why did you say that the light object would hit the ground before the heavy object if I dropped them? And Elise gave me the following answer. He said, well, if there was 2 bags of garbage in the kitchen, a little bag of garbage and a great big giant bag of garbage, and Ma told you to take them downstairs to the garbage can, which bag would get there first? Very smart. What Elise appreciated was that it was harder to move the heavy object. You know, it's easy to move light objects. It's hard to move heavy objects. And if it's truly harder to move heavy objects, remember the Aristotelian idea was the heavy earth wouldn't move at all. If that's truly true, then it should be. The light object should fall and hit the ground first and leave the heavy object hanging up there in space by its inertia, which is a fancy word for saying heavy things don't want to move. Now, what we can do is we can take the two philosophers, each imperfect, Elise, my sister, and Aristotle. Elise says that the light object should hit the ground first. Aristotle says the heavy object should hit the ground first. They're equally wise people. We don't know who to believe, so we add them up and divide by 2, and what do we come out with? That the heavy and the light object will hit the ground at the same time. Now that seems like a strange story, but it's exactly what Newton did. You see, the next important person, and I've told you that all the smart people in the world have thought about this question, heavy and light objects, why they hit the ground at the same time. The next wise person after Galileo to really think in depth about this was a man called Sir Isaac Newton. And Isaac Newton wrote the following formula. This is Newton's law. Here it comes. It's an algebraic law. It says that the acceleration of any object is equal to the force on the object. Isn't that right? More force, more acceleration. You know, bigger engine, more engines, more kick, more push, more acceleration. So as F gets bigger, A gets bigger. So the acceleration is equal to the force, but it's divided by the mass of the object. Now, if you have the same engine in a car, but you put more fat people in the car, what happens to the acceleration? The more people you put in the car, does the car accelerate faster? Hell no. The more people you put in, the slower it accelerates. The more weight you put in a train, the harder it is to accelerate the train, the harder the load. So as M gets big, what happens to A? A gets small. Why? Because M is in the downstairs part of the fraction. Isn't that right? It's called the numerator and the denominator, but who cares? As the downstairs part of a fraction gets bigger, it makes the fraction smaller and makes the A smaller. And this is Newton's law. Acceleration is equal to the force on an object divided by the mass of an object. Now let's apply that to a rock. Let's suppose you have one rock and you drop it. There's a force on the rock, and the rock has a certain mass. Force is 1 pound, the mass is 1 pound. The acceleration is whatever the acceleration is. Now let's make the rock twice as heavy. If we make the rock twice as heavy, what happens to the force on it of gravity pulling it? Oh, the force is twice as much. F becomes 2F, twice as much force on it. But what happens to the mass of the object, the heart? It doesn't want to go. It wants to be lazy. It wants to be lethargic. What happens to the mass of the object? If you make the rock twice as much rock, the mass goes up by 2 too. So we have twice the force and twice the mass. But what do the two 2's do? There's a 2 upstairs and a 2 downstairs. They cancel out. And what are we left with? The old F and the old M. They cancel out. This is what I've done is nothing what Newton's done. What Newton did is nothing than combine the story of Aristotle and my sister Elise. Aristotle saw that the F gets bigger and thought the acceleration should get bigger. Elise, my sister, saw that the M got bigger and thought the acceleration should get smaller. What Newton did is he saw them both, that they would cancel out in this algebraic relationship. And there's Newton's explanation of why heavy and light objects fall down or accelerate downward at the same rate. Doesn't make any, the mass of the object doesn't make any difference. But Newton was not the last person to think about this. As I said, every wise person that's come along has thought about this very question. And the next wise person who thought about gravity, who came after Newton, quite a while after Newton, was who? Albert Einstein. And Einstein thought about this very same thing. And now I'm going to give you Einstein's explanation of why heavy objects and light objects fall at the same speed. Now you think it's going to be complicated, don't you? It's kind of Einstein's theory is going to be complicated. No. Everything is straight in a kinky way. This is Einstein's explanation of gravity. Einstein says this. He says, well, if you drop something, and there's a table here, at first there's a big distance between the table, and then it gets smaller and smaller, and finally the object hits the table. Of course, the same thing would happen. It would be exactly the same. Suppose when I let go of this, it didn't fall. Suppose it just stood there. And suppose the floor came, the table came up. Wouldn't it be the same? That they get closer and closer, and then they would hit. And not Newton, Einstein says, there's no way to tell if the object falls down or if the floor comes up. In other words, Einstein says gravity can be made by having the floor come up just as well as having the object go down. You see, this is this idea of relativity. You can't tell who is moving. Now, I want to ask you a question. Where do you suppose Einstein got this idea from that gravity could be made by having the floor come up? Where do you suppose? You'd like to think that these people talk to God, isn't that right? Like Moses, he goes out on the mountain and God gives him the message. But of course, that isn't it. So where in the heck did Einstein get the idea from that gravity could be made by having the floor come up? I'll tell you where he got the idea from. When you're a little kid and you get into an elevator with your mother and the elevator begins to go up and somebody hits the up button and you're a little kid and it's a fast elevator, all you go, in the olden days, elevators, by the way, now they accelerate gradually. They're controlled electronically. But in the olden days, they used to accelerate pretty brutally, some of the big ones. And you go, and you'd feel yourself weighing more. Why were you weighing more? Because the floor in the elevator was coming up. And so Einstein got the idea that maybe all of gravity, not this extra gravity, but all of gravity could be made by having the floor come up. Same thing and you can do the same thing. You can weigh less in an elevator by pushing the down button, and you weigh, your stomach comes up, and you can get the gravity of the opposite kind. If you really want to play with this idea that objects don't fall, but the floor comes up, you can get some amazing results. I'll show you two amazing results. One is pretty obvious. If you have Galileo's 30-pound melon and his 15-pound melon, and you believe Einstein's theory of gravity, and Galileo lets go of the two melons, what do? The two melons don't fall, they just stay there. But the floor comes up. Well, if the floor comes up, which melon's going to get hit first? Of course, they're both going to get hit at the same time if they're at the same level. So obviously, the weight of the object doesn't have anything to do with it if objects don't fall. I'll tell you another amazing thing that can be explained from Einstein's theory of gravity. This is always as amazing to me, but if you have a pistol, an old .22 revolver, you fire it exactly, you don't fire it up, you don't fire it down, you just fire it horizontal level. You're out in the desert, Nevada, flat, boom! No bullet's going to go out. Sometimes it'll go out a mile, at least a mile, and finally it'll hit the desert out there, fly along level, gradually descending. In this hand, you hold another cartridge, and when you fire the gun, at the same moment you release this cartridge. Now, it isn't going to go a mile out in the desert. It's going to fall right down here. And they tell you this, believe it or not, which will hit the ground first? Well, it turns out the physics book, or Ripley's Believe It or Not, will tell you that the two hit the ground at the same time, which is astonishing because the bullet you fired goes out a mile before it hits the ground. The one you dropped right here hits the ground a foot or two from your feet. How could it just go down there and hit the ground at the same time one goes a mile out before it hits the ground? It's hard to believe. But if you take Einstein's theory of gravity, it's not hard at all. Because one bullet just stays there. Which one's that? That's the one you dropped. It doesn't do anything. It just stays there. And the one you fired, all it does is fly out on a level line. Isn't that right? And the level line is at the same height as the bullet that's just standing there. And what does the floor do? The floor comes up. Which one's it going to hit first? Well, they're both on the same line. The floor comes up like this. It's good. Hit them both at the same time. Well, it's not hard to believe at all if you take Einstein's theory of gravity. Finally, I'll tell you something else about Einstein's, the most amazing thing of all about Einstein's theory of gravity. Einstein figured out that gravity would not only affect things like bullets, but gravity would also pull on light. Oh, gee, how did he figure out that gravity would bend light downward? He must have known one heck of a lot about light, more than anybody else did. And he must have known one heck of a lot more about gravity than anybody else did. And Einstein must have reasoned out that somehow there was some powerful, strange mathematical thing about light and some other powerful, strange mathematical thing about gravity, and the gravity reached around and grabbed light when nobody was looking. He figured it out. No, remember I told you, these people who say these things work by magic equations are off the track. The thing works by a story. You have to have the right story, just like Galileo had the right story. And the story of gravity that Einstein had is that the floor comes up. Now, let's look at this. Let's apply that to light. Suppose a light beam. Let's pretend that this blackboard is a room. Let's pretend we have a hole on one side here and a hole at the same height. See, these holes are both 1 foot above the floor, and you put in a flash of light. Maybe there's a flashlight over here. Flashlight flashes in some light. Light goes across the room and go right out this hole. Isn't that so? Well, let's suppose in the meantime that the room begins going up. Light might get in that hole, goes across. But by the time it gets across, is that hole still going to be there? That hole's attached to the wall, isn't that right? The wall's attached to the floor. Be up there. This whole thing will be up. So where's the light going to hit? It's going to hit down here. Now the people that are living inside the room, what do they think? They think, oh gee, the light came in here, and then it hit over here. And they think, holy cow, gravity must have bent the light. Gravity bends light. All so far as we've gone in this thing, all comes from just imagining that gravity is due to the floor coming up. But there's one little problem with that idea. If you take it just literally like that, you get into trouble. And for this reason. You ask, how far is it to China? Well, through the center of the earth, it's about what? 8,000 miles to China. If the floor is coming up here, and there's some professor in China, he's teaching physics too and giving the same lecture, and he says the floor is coming up there. Well, if the floor is coming up here and the floor is coming up there, then if it's 8,000 miles to China now, by tomorrow morning, it's going to be something like 80,000 miles through the center of the earth to China. But we know tomorrow it'll still be 8,000 miles to China through the center of the earth. So it can't really be that the floor is coming up in China and really be that it's coming up here at the same time. But somehow it acts as if it is. And the trick of Einstein's theory of gravity is to remove that essence out, to make it possible to think that the floor is coming up here and the floor is coming up there. And the way Einstein does it, I'm not going to go into this, but his trick is that when the floor comes up, it has a certain peculiar effect on how time works in the room. And what Einstein does is he says, well, the floor doesn't really come up, but time in the room works in the same way as if the floor were coming up. And by that means, he's able to explain gravity. But the essence of it is locally, that if all you could do was just experiment in this room, you could never go to China, there'd be no way to ever do a test in this room and tell if there was gravity or if the floor was coming up. That is indistinguishable. Just like Galileo's story. Remember, Galileo said there's no way to tell if the ship is moving towards me in the dark or I'm moving towards the ship in the dark. In the same way, the same idea holds for gravity. Now back from Einstein, all the way back through Newton, and all the way still further back to Galileo and the story of Galileo. Galileo has told about gravity, and he has told how gravity works. He said, gravity works in this way. Heavy objects and light objects, if they're heavy enough that you can forget about the effect of the air. And by the way, if you were on the moon where there was no air at all, then you wouldn't have to worry. All objects would work the same. In fact, one of the nicest experiments the astronauts did when they got to the moon was they dropped a hammer and they dropped a chicken feather out on the surface of the moon. And on the moon where there is no atmosphere, the chicken feather hit the ground at the same time that the hammer did, a heavy iron hammer. But that describes how gravity works. What Galileo was a scientist, and he wanted to know why it works that way. Remember with the telescope, Galileo knew how the telescope worked. You put the negative lens near your eye and the positive lens far from your eye, and it works. But besides knowing how it works, Galileo wanted to know why it worked that way, and that's why he came up with the story of the cow's eye. And so also with gravity, Galileo didn't want to know. He wanted to know how it worked, but he wasn't satisfied. Beyond that, Galileo wanted to know why it worked. What made the force of gravity, he wondered. Now, it's quite a mystery as to what makes gravity, because you can't see what causes the force, the pulling force. You know, if you're pulled on by a rope, you can see the rope. If you're pushed on by a person, you can see the push. Usually when a force works on you, you can see what is making the force. You can see the horse. You can see the wheel turning that's pulling you. But in the case of gravity, the force comes and it pulls down the apple, but you can't see what's making it. So Galileo wondered what could be the agency, what could be pulling on these rocks, on these melons, what could be making things fall. And he says it must be, the agency of the force must be something that you cannot see. And Galileo thought to himself, what is the most common thing that I know about that exerts a force on things, but you can't see it? What is an invisible agency of force? And he thought, and then it occurred to him, the wind. The wind is invisible agency of force. And Galileo got the idea that the cause of gravity is a wind, and that this wind comes from space and blows down towards the center of the earth. This wind is drawn in from space into the center of the earth, and that objects get drawn in by this wind, and that's what makes objects fall. The drag of the wind on objects pushes them towards the center of the earth, just like the wind blowing on a leaf moves it along ever faster and faster. And so this wind blowing into the center of the earth draws things down and is the cause of gravity. And Galileo actually wrote an article in which he explained how this worked, that gravity was caused by a wind. This was Galileo's theory of gravity. But then Galileo got to thinking, and he became unsure. And then he thought some more, and he became even more unsure. And then he thought some more, and finally he decided, no, that won't work. The explanation that gravity is caused by a wind will not work. And I'd like you to see if you can think of what Galileo might have thought of. I'd like you to think about this to see if the wind explanation of gravity can be made to work or can't. Maybe it can, maybe it can't. But I'd like you to think about that and see what you come up with. And next time I'll talk about the wind theory of gravity and what's right with it and what's wrong with it.